असतो सकमया तमसो मा ज्योतिर्गमया मृत्योर्मामृतं गमया ॐ सहना भवतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः.
Hello everyone, my name is Ajuna, your host of today's event. First of all, happy Pi Day to one and all. We are very, very happy to have this webinar, our 14th national webinar of Maths Aspirants today on a special day where mathematicians feel it's a very special day. And today I welcome you all who have participated already and those who are participating later because the Ramzan event is going on. I welcome you all wholeheartedly to the program, and I request you to do an active participation and you stay energetically even though it is an online program. So wherever possible, utilize, if it is a text box chat thing or if there is a chance to speak, you take up the chance and be part of the program. And now we are gonna talk about Maths Aspirants. Most of you already know about Maths Aspirants. I am a part of Maths Aspirants from the beginning itself, and I am so honored to be a participant of the family. I will say family because now it has become a family. We have our guardian, Dr. Vinod Kumar P, Associate Professor of Mathematics, TMG College, Tirur, Kerala. And Sir started this wonderful family or community as a WhatsApp group in 2017 to discuss mathematics, to do problems for students. But later, because of a good participation, it slowly began to grow and more groups are formed. And now we are in newspapers, online. If there is a program, people are knowing about it, and we have a good participation nationwide or maybe from different countries also. So this is not a small thing. It's like it's a hard work of many people who really want mathematics to be promoted and want to help each other. So this is a good platform. If you have already joined, you know that. And it is like a home to discuss mathematics and to support each other. Okay, so with that said, I am so happy that it's our 14th national webinar and it is happening on March 14th, which is Pi Day also. And today we have some honorable teachers and very senior and we are very happy to have these teachers here. First, let me tell about our key speaker, Professor Madhavan Mukund, Director of Chennai Mathematical Institute and Professor of Computer Science. He is our speaker of the day, and I'll say a super speaker of the day. And we have the topic computational thinking. Computational thinking is something nowadays like a fire, like everywhere it is using. And if you are a mathematician, it's an essential skill nowadays. But I think some people actually don't know about computational thinking. That is my thinking, because even I was not exposed much about these computational thinking, programming, and how it is related to mathematics a few years back. Now I know, and I know the importance, and I also personally like very, very much to know more about it. So in the same way, I think all the participants who have joined today on a weekday will be having the same mentality to learn, to understand more about computational thinking. So it's a very relevant topic that we have today. And I express my sincere gratitude and all our respect to Professor Madhavan Mukund for sparing his valuable time and coming here for delivering a speech for us. Welcome, sir. Welcome to our program.
Thank you.
Okay. Now we have a very nice professor for introducing our key speaker, Professor Tamban Nair. He was formerly professor and head of Department of Mathematics, IIT Madras, and currently a visiting professor in the Department of Mathematics at BITS Pilani, Goa campus. So he's joining us today from Goa, and we are so happy and so grateful for Tamban Nair sir to be here. Welcome, sir. Welcome to the program.
Yeah.
Okay, and with that said, with all these blessings, I hope some more teachers will join on the way and use this opportunity as much as possible. And once again, I wish you all wonderful Pi Day, and you are all utilizing the Pi Day and honoring it with by attending this program. Now I'm going to welcome Dr. Vinod Kumar P, our everything, our pillar, our guide, who is working so hard to make every event that is happening to be a success. And he's going to say a few words to us before starting the event. Welcome, Vinod, sir.
Thank you, Ajuna. Dear friends, happy Pi Day to everyone, and hearty welcome to the 14th webinar organized by our group. We math aspirants usually used to celebrate 3 particular days like National Mathematics Day, Pi Day, which is also the International Day of Mathematics, and our Independence Day with invited talks by professors from premier institutes. Today, this auspicious day, we are really blessed to have Professor Madhavan Mukund, Director, Chennai Mathematical Institute, with us to have the webinar on computational thinking. I'm sure that today's session will be really fruitful and informative to everyone gathered here. I would like to express my sincere thanks and gratitude to Professor Mukund for accepting our invitation and joining with Math Aspirants. And also I would like to share my gratitude to Professor Tamban Nair sir for being with Math Aspirants. Also, I take this opportunity to thank and express my gratitude to all Math Aspirants community for being with me throughout these programs. I welcome everyone to this program. Thank you.
Thank you so much, sir. Now, without any delay, I'm going to call Professor Tamban Nair sir to introduce our speaker of the event.
Yeah, good evening. I'm very happy to welcome Professor Madhavan Mukund, the speaker of today's event. Professor Mukund, as I already mentioned, he is the present director of Chennai Mathematical Institute, generally known as CMI. Professor Mukund is a renowned computer scientist who did his BTech in computer science from IIT Bombay in the year 1986. Incidentally, it was my alma mater also. I did PhD from IIT Bombay, left in 1987. Beginning, I left after my post PhD, I should say, post doctoral research. Anyway, so he did his PhD from Aarhus University, Denmark, in the year 1992. His research interests include models for concurrent and distributed systems, formal verifications, and distributed algorithms. And these are some of the thrust areas of computer science today, which I hear from my colleagues in the campus and other places. He served as president of Indian Association for Research in Computing Machinery. Also, he was an elected fellow of the Indian Academy of Sciences from 2018. He has been the national coordinator of the Indian Computing Olympiad since 2001. Professor Mukund has more than 50 research papers in reputed journals and refereed proceedings. As some of you may be knowing, in computer science, conference proceedings are sometimes rated much higher than even many of the journal papers. Okay, so and also he's author of a book titled Computational Thinking, a primer for programmers and data scientists. That happens to be today's title of today's theme of his exposition also. So with this short introduction, I invite Dr. Mukund to start his exposition.
So thank you so much. Thank you for the kind invitation. I'm so happy to be able to join for this very special lecture on this very important day. And I also am very happy to see such a large number of participants have joined. So I hope that what I have to say will convey something useful to many of you. So let me start. So the title of today's talk is Computational Thinking. And as Ajuna said, this has become quite a popular term. And it is not very precisely defined, and it means different things to different people. I will give you one kind of perspective on this, which is a little bit more from a traditional computer science perspective. But let me start by showing you an interesting article which came in this online magazine called Quanta. It's a very, if you have not come across Quanta, I would recommend that you look it up. Quanta is supported by the Simons Foundation, and it's probably, I would say, the most interesting and relevant magazine reporting on advances in various sciences, mathematics, physics, computer science, biology. It's online, free, so please look it up. But anyway, so about 6 months ago, I was supposed to give a talk on the similar topic in a college, and I came across this coincidentally the night before my talk. So I thought it was useful to put it. So if you cannot read it, let me read it out. So it says, do you ever strategize about ways to speed up your commute, repack a suitcase to free up some room, or tweak a recipe to get food on the table faster? Then you are thinking, that's you thinking like a computer scientist. So essentially it says that physicists and philosophers may be content to ponder on the nature of space and time, but for theoretical computer scientists, space and time are scarce resources, and they try to cook up ways to make the most of them. So really, computational thinking is in some sense about doing things which optimize the use of the resources available to you, in particular space and time. So with this kind of generic introduction through that article, which I think is quite interesting because it talks about very day-to-day things, right? So computer scientists are actually solving problems which are abstractions of very fundamental tasks. Like when you say packing a suitcase, it could also be packing some things into a truck to transport. So how do you efficiently transport things from one place to another? Or how do you, put things together in such a way that you optimize the timetable and so on. Right? So essentially, computational thinking is about taking a task which has to be performed and finding a systematic way to do it, first of all, and also doing it as efficiently as possible so that you minimize the resources that you use. And very often the resources are time and space. Most often time is of the essence because you want to complete the task within a given period. So if you're supposed to decide how best to pack your truck for moving, you cannot spend 2 days deciding how to move it because you need to move, right? So you need to do these tasks in a timely manner. So this applies to any number of real world tasks, but we will restrict ourselves to the tasks which normally come up in a traditional computational framework, which is that you are doing something with information. Yes, there is a question you can ask, or you can unmute or whatever. Kumari? Hello.
Sir, we can move.
Anyway, so I'm also keeping the chat open. So if somebody puts the chat question, I'll be happy to answer from the chat also. So we are talking in a specific setting now about processing information, right? And information is probably the most important quantity in our lives these days. We get information from so many sources. Everything that we consume on social media is in some sense information, but we also get bombarded by information from media when we watch something on the screen. There is a lot of information, newspapers, everything has information. But we have a lot of personal information also, right? So we have contacts, on our phone, we have our appointment calendar, we have various things that we collect about our finances and so on. So processing information is the bread and butter of computation. And today I will talk about computational thinking from that perspective, which is more, as I said, traditional computer science. But many of these ideas can be applied in many different contexts. So when you look at this question about processing information in an efficient and systematic way, right? You have some common ideas which come up across different problems. And this, as I said, is the part which is called computational thinking, which is kind of hard to define. So it's more easy to explain through some examples, and that's what I will try to do today. Okay? So first of all, so this means that you have to organize it in some manner. And these are what computer scientists call data structures. So you need to put your information or your data into some format where you can retrieve the information easily. And then, of course, if you want to change it, you must be able to update it easily. Then you need to take this information and do something with it. You have to answer some questions. Right? So you need to process it. So for doing this, you need some procedure, some steps. And this is what we call algorithms. And finally, sometimes before you do the main task, you need to do other tasks before that to make your main task easier. So this is a special part of this algorithms thing called pre-processing. So we will try to address some of these ideas today through some very straightforward examples. So it may look like the examples are very basic, but I think the ideas are also very basic, but they're fundamental. And I think it's good to start with basics so that later on, when you come across them in different contexts, you have a clear idea about what is going on. So it was mentioned that along with Professor G. Venkatesh, I have written a textbook on computational thinking, which says a primer for data scientists and programmers. So this was in the context of an online course, which we teach jointly for the IIT Madras BSc program. And the outcome of that course was this book. And the main kind of principle that is followed in that course and in the book is that we teach computational thinking by looking at simple problems involving data. And so here is something which many people might find somewhat relevant to them. So IPL is starting in about a week. So this is some data about last year's IPL. Okay? So first of all, we can see that it is organized in some particular format. And this is very typical these days. We find it organized in a table. So you might get it in the form of a spreadsheet, or you might see it in a newspaper in the form of a table. And then it has some information, right? So it has some information, and the particular information it has, so you don't see all the rows because they don't fit. But it starts with the first match of the season and goes to the last match of the season. And for every match, you have some information about where the match was played, who are the two teams that played the match, who won the toss, who won the match, and what was the target set by the team batting first. Right? So team 1 is the team that batted first, team 2 is the team that batted second. So you can infer some things from this. For instance, if you see in the first match that team 2 batted second and CSK lost the toss, then you can assume that RCB won the toss and chose to bat. Okay? So in this sense, in the second match, you can see that Punjab won the toss and they chose not to bat because they batted second. So there is a lot of implicit information also, but this is the kind of data that we would like to now process using some systematic things. And I'm going to ask some very simple questions. Okay? So first question, very simple question. How many matches were actually played in the IPL, including all the eliminators and the qualifiers and the finals at the end? Okay? Then maybe I might want to ask, across the season, what was the largest total that anybody was asked to chase? What was the highest target? Overall, I might ask, on an average, what was the target that was set? Then I might ask, how many matches had targets which were above this average? Right? So these are all questions. It's not necessary that every single question might come to you naturally, but you might ask, and these are typical of the kinds of questions that you might want to know, and you have to extract it somehow from that table. So you need a way to deal with these questions in a systematic and somewhat efficient way. So first, I will just go through these questions and explain how you would do it. Of course, we know how to do it by hand because this is not a very large table, but the same principle applies even if this was a table not for one season of IPL, but maybe for, over 100 seasons once something runs for a long time and it's too difficult to do by hand. So let's start with the first question, right? So how many matches were played? So as we said, there is a row in this table for every match that was played. So really we are asking, counting the rows. Now, if this was given to you directly as a spreadsheet and you opened it in a spreadsheet software, you would have the row numbers on the left and you can just look at the row number of the last row and decide from that how many rows are there. You might have to subtract one because the header row might be numbered 1, but more or less you can read it off directly from the screen. But supposing it was given to you in this form without being presented through some software like that, then you have to actually go through the table from beginning to end, right? So if you go through the table from beginning to end, you have to organize the table in such a way that you can see where the rows are and where the columns are. So usually, although we see it as a kind of a matrix, a two-dimensional thing where we have rows followed by rows followed by rows, and each row has a fixed width. Normally, we would think of this as a sequence of rows, so a list of rows, and each row has some internal structure, right? So it has, in this case, 6 parts, right? It has the city, the first team, the second team, who won the toss, who won the match, and the target, right? So we would have this information presented to us as this kind of a list where we have a list of rows and each row has this structure. And what we want to know essentially is how many rows there are. So we have to start from the first row and keep going until we reach the last row. So this brings us to the first important concept from computational thinking. So this is an idea of iteration. So iteration just means go through a sequence of things from beginning to end, systematically going from one to the next until you reach the last one. Okay, so this is a fancy word, but it just means doing a sequence of things where the sequence is given to you. So you are processing a sequence of items from beginning to end. Now, what do you need to do when you're processing this? You need to count. Right? So if we were doing it in our head, we would just start, and every time we see a new row, we just count, like the way we do counting when we are counting anything, right? So we just keep a count mentally. But now we are doing it in a way where we are not doing it ourselves, but we are giving a procedure to do this. So we have to maintain this information somewhere. So that's why we need these kinds of intermediate quantities to store information. Right? So we need to process the number of rows. So we need to keep a track of how many rows we have seen. So we keep a counter. Right? So we can call it whatever we want. We can call it X or Y, or we can give it a meaningful name. So we keep a variable whose name is count. So variable in this sense is slightly different. Okay, so it's different from a variable in mathematics. Right? So when I say somewhere in a mathematical argument, if I say let X be a number, right? So in this context, X is a variable. I will go on to write something about the value of X, suppose X is even, suppose X is odd. But notice that when I say let X be a number, I'm not telling you what number it is, but it is a fixed number, right? So throughout my further exposition about X, I am not going to change the value of X. So if I imagined X to be something, it remains the same. So in mathematics, a variable stands for a fixed but arbitrary quantity. Okay? So it is something whose value doesn't matter, but the value is fixed once and for all for the rest of the argument. Now, in this kind of computational thing, a variable is actually something which can be updated. Right? So it's actually a placeholder where you can keep a number and we can change that number depending on what we want to do. So that's what we mean by a variable. So you keep this variable count, and what do you do with it? Well, initially, there are no rows that you have seen. So you initialize the thing saying, I have seen 0 rows. Right? And now as I go through this table, every time I go to the next row, I will add 1 to count. I will increment it. In this way, count keeps getting updated. And at the end, I just have to report the value of the count, right? So this will automatically be the number of rows that I went to, skipping one at a time. So it's very straightforward, but the intention is that it should be straightforward, right? So the whole point is that you don't kind of look at the table and guess, or try to do something fancy like count in 5s or count in 10s to speed up, because you may make a mistake. One group of 5, you might accidentally skip one and make 4 or 6 or something. Right? You just do one at a time, do it systematically, go from beginning to end. You go through this table once, from one row by row, and you're done. Right? So this is a very simple question. It has a very simple solution, but it illustrates a couple of things. One is that question about how this information is given to us. It's given to us as a sequence of items, and these items in this case happen to be rows. So notice that in order to count the rows, I don't need to look inside each row. I don't need to know who was the team playing in that match, who won the match. I just need to know that each row is a match. Right? So I don't need to look at the inner structure of each row in order to count it. And the other part is that you need some intermediate quantities like count in order to keep track of your computation. So you need some values which get updated as you go along. So this was the first question that we had asked: how many matches were played? The second question is also intuitively not hard to solve, but the question is, how do you do it systematically? So the question here is, in which match, or what was the highest chasing total that was set in this season? Okay. So what we need is in the last column is the run target. We want the largest value that is seen in the run target. Right? So if you look at the first few rows, you can see that there is a 209. Right? So it suggests that maybe 209 is a good target. But if you go down, then you start seeing bigger values. Right? So you see suddenly a 278, for instance. So is 278 the biggest value? We don't know, because anyway, this is not a complete table because there are some dots in the middle. Right? So how would you do this? Right? So in this case, you have to do something slightly different from counting. So again, we want to go through all the rows. But as we go through the rows, what we want to do is we want to keep track of the maximum value that we have seen so far in the last column. Okay. So for doing this, so earlier we were keeping a value count, which was updated by adding 1 every time we went to a new row. Here instead, what we need to keep track of is what is the largest value that we have seen. And if we see a larger value, we must update it. So we have to maintain a variable again, but this time let me call it max, because for maximum. Okay? And this is supposed to represent the maximum run target that we have seen so far. So in the earlier case for count, we started off by saying that we have seen no rows, so we started off with a value of 0 for count. So similarly, we have to think of what should be the value that we start off for max. Okay? So we know that whenever we see a score, it must be something which is bigger than 0, right? You can't have a cricket score which is negative. So if we start off by saying that I believe that the value of the maximum is 0, you can be sure that any real match will have a higher score, so you will get a valid maximum after that. You will not miss out on it. So supposing I start off by saying I believe the maximum is 300. Now, if no match actually has a score which crosses 300, you will never find out what was the actual score, because every time it will say that 300, the maximum I've seen so far, is bigger than the maximum I've seen. So it's important to initialize this correctly. So best thing in this particular case is to initialize it to 0, because you know that every match score has to be bigger than 0. And now what you do in the iteration is that, so yeah, so the other thing that you can do is you can just start by looking at the first row and say, okay, the first row, when after the first match happens, the maximum is whatever was set in the first match. Right? So this is also something you can do if you don't know what could be the values. So this is now the operational part of our computational thing, which is what do you do when you read a new row? So here, unlike the count case, we have to look at the last column. So we have to extract the run target from the row. So we have to expand the row out into its 6 parts and look at the last part. And then we check. Okay, so we have assumed something is the target so far. In this case, after the first match, it is 174. So now when we come to the second match, for instance, right? So when we go from 174 to 175, Okay, then we will see that, okay, I've currently believed that 174 is the max. Now I see a 175. So I have to replace my assumption about what is the max by 175. Then I will go to the next row and it will say, oh, 175 is no longer the max. 209 is the max. Now I come to the next row and I see 194, but 194 is smaller than what I have seen before. So I will skip it and keep my max as 209. Right? So in this way, I will keep going, and 207 and so on. And now here suddenly, when I come to this point at 278, I will again revise my max to 278. So this is what we do in this case, right? So for each row, if the current target exceeds the max, we update the max. So again, like last time, in the first problem, at the end of the iteration, the value that we got in our variable that we were keeping track of, in that case, it was count, gave us the total number of rows. And here the same thing happens. The value max that we are keeping track of has the largest number that we have seen across all the rows. And therefore, this is the maximum target which was set during this system. Okay. So I will leave this for you as an exercise. How would you do the same thing if your goal is not to find the largest target, but to find the lowest target? Right? So just think about it, just to see whether you have got a clear idea about what's going on. This is not very complicated. It's just to give you an idea about how to proceed. So our third question asked about the average. Right? So we know so far how many are there. We know what was the highest. So what is the average? Right? The average is always the total divided by the number. Right? We have to add up all the targets across all the matches and divide it by the total number of matches. So we need the overall count and the total sum. So of course, we know how to find the overall count. Right? So we can go through this whole thing once and we can count how many matches were played and we are done. How about the sum? Well, we do now a similar thing, except in count case, we started with the count equal to 0, and for every row, we just added 1 to indicate that one more match is played. Instead, here we will keep a track of the sum, the total of all the run targets. So again, we will say 0 when no matches have been played. Totally, I've seen no target. But every time I see a new match, I take the target of the current match and add it to the sum. Right? So that's how you compute the total. You just add the ones one at a time. So at the end of this thing, we just take the sum and divide by count. So this is again a situation where we have gone through this, but notice that it looks like we have done 2 iterations, right? So we did 1 iteration here to count, and we did 1 iteration here to find the sum. So we had to go through this table twice. So you might ask yourself, for example, so remember that one of the principles of computational thinking is, so far, one thing to emphasize is that we are doing very boring things. Okay, so computation at this level, when you're doing things systematically, there is nothing clever about it. So you're just making sure that you don't miss anything. Right? You do things systematically, you count systematically, you add up systematically, don't skip a row, don't do anything clever. Right? But we might ask ourselves, can we do it a little better? Right? So why are we forced to do 2 iterations? Is it possible to do this without reading the table twice? So the general question is that if I want to find the average of some sequence of numbers where I don't know the number of, I don't know what is n, right? So what we are saying is, first we have to go through the thing and add up the numbers, and then we have to separately go through the thing and find out what is n. Right? But if you think about it, you can actually do this in 1 iteration, right? Because if I have so if I computed this sum, right, and if I know that the number of things. Okay, so the average up to I. Right. So I know, supposing I know the average at I, and I know I, and then I see xi plus 1. So what is the new average? Right. So the new average, of course, is sum x1 to xi plus 1 divided by I plus 1. But I don't have that sum because I don't want to go back and calculate it again. But I know that this sum is equal to the average multiplied by I, right? So therefore, I can compute that summation. I can add the new xi plus 1, and I can divide by I plus 1 because I know what I is. So in this way, every time I read a row, I can just increment the average for that row by 1 at a time. Okay? So this is what I was saying by saying that you can collapse this whole calculation to a single iteration and update the count and the sum with each row. So it's not very complicated, but it's an illustration of the kind of things that you worry about if you are computing, right? So am I doing too many things? Do I need to do them? And so on. So the fourth question that we asked said, okay, how many matches had a target which was above the average that we computed? Right? So here we have to first compute the average, because without knowing the average, we can't tell whether something is above the average or not. And of course, if we have reached the ith match, maybe it is above average so far for the first I matches, but the average may change later on. So the status of match I, so match I may be above average for the first I matches, but it may not be above average for all n matches. So unless you have computed the average of all the n matches, you cannot really decide whether the ith match is above average or not. So here, so in the previous case, we said that you did 2 iterations, one to find the count and one to find the sum, but you could actually collapse the 2 iterations into one by finding the sum incrementally as you go along and finding the average incrementally as you go along. But here, I'm arguing that you cannot do that. You have to find the average first. So you have to do one pass of the table to find the average. And then you can do a second iteration to compute which matches are above this average. Okay? So there's a difference between the previous one and this one, in the sense that in the previous one, the 2 iterations could be collapsed, and here the 2 iterations cannot be collapsed. Okay? So that's the main difference. But here a little bit more happens. In the previous 2 cases, both in the case of the count and in the case of the max and in the case of the sum, for every row you made an update. Right? In the case of the count, for every row you definitely did a +1. In the case of the max, for every row you looked at it and decided whether to update the max or not. Right? Now here we are going to count, but we're only going to count if the row is above the average. So the count will happen not in every row, but only in those rows which meet some criterion. So it's like, if you are passing your data through a filter, right? So this filter is pulling out those matches which are above the average and passing through all the matches which are below the average. So in the end, you end up counting only those matches which pass this filter, right? So this is sometimes called a filtered update. So you have essentially an iteration, and then in the iteration, you have a conditional update. And this forms the bread and butter of many of the standard computations that you do, and a lot of them are just of this form. So we can ask more questions like this. So we can ask, for instance, very often people say, oh, we lost the toss. So the question is winning the toss an advantage? So how would you compute whether winning the toss is an advantage? Right? So we know in each row we have toss 1 and match 1. Right? So we know who won the toss. Right? So if this is the same as this, then the team that won the toss won the match. Right? If this is not the same as this, then we know that the team that won the toss lost the match. So if you want to know whether winning the toss is an advantage or not, we can go through the rows and check in how many rows the winning team is the same as the toss winning team, in how many rows is the winning team different from the toss winning team, and then look at, for example, you might just want to see, is it more than 50%? Or if you want to really think of it as an advantage, you might say that, is it at least 60%, is it 70%, and so on. Similarly, you might ask, okay, we talked about the average target overall. We talked about the highest target overall, but some grounds are smaller, some grounds are bigger. So for example, which are the grounds where typically the scores are high? So in this case, what you would have to do is you would have to group together the scores. You would have to say, what are all the scores for Chennai? What are all the scores for Mumbai? What are all the scores for Delhi? And then one simple way is to just, here you will just, and when I group, I will also sum them up. So I will take all, if I just take the total number of matches played and then divide by the number of matches played there. So not all places have the same number of matches. If you think about that table, you would see that the final matches were played in Chennai, even though Chennai was not there in the final, right? So therefore, the number of matches played in each city is not the same. So it's not enough to just take the total number of runs scored at a venue, because you need the average run, but you need the average per venue, right? So it's a little more complicated than keeping one average. You have to keep multiple averages, which are somehow indexed by the venue. So all these things become part of the calculation. So with this background and this kind of simple example, I want to get to something slightly more complicated involving the same kind of thing. So supposing I have a similar table for the previous year, right? And every year when a match comes, we are interested in knowing, oh, last year what happened when these teams met. Right? Will they, last year they lost, will they win this time against? Are these opponents difficult opponents? Are these opponents simple opponents, right? So we might have to ask the question like this: how many head-to-head contests flipped between 23 IPL and 24 IPL, right? So in 23, say Mumbai played Bangalore in Bangalore and Mumbai won. And in 24, Mumbai played Bangalore in Bangalore, and this time Bangalore won. So then in that case, the head-to-head flipped. So what we need to do is look at the same match or the same pairing across two tables. Right? So we need to match the rows. We need to look for a row in table 2023, and we need to look at a similar row in table 2024. And similar means that the two teams are the same and the venue is the same. Okay. So the match in Bangalore between Bangalore and Mumbai, who won in 23, who won in 24. And if the same team won, then the match did not flip. If the same team did not win, then the match flipped. So this kind of thing requires us to match every row in table 23 versus every row in table 24 to check whether the same thing, because there could also be a situation where some teams played in 23, did not play in 24. Some new teams came in 24, did not play in 23, and so on. Okay? So this is what you typically have to do. So we are counting the number of flipped matches, that is matches where the results changed from 23 to 24. So we initialize a count to 0. And now for every match in 24, okay, we look at, so we have the 24 table. Right? And then we have the 23 table. Okay? So now we look at the first row here. So the first row maybe is, we saw was, I think, Chennai versus RCB in Chennai. So now we don't know when Chennai played RCB in Chennai in 23. So we have to go down this whole table looking for that. And then somewhere along the way, we will find it. Okay, so this was the place where Chennai played RCB in Chennai. Now we look at the outcome, right? So when we find that the home and away teams are the same, that is, it is the same situation, and the result is reversed. That is, in one case, one team won and the other case, then in such a case, we'll implement it. Okay? So we have to basically scan through this thing row by row, and each time I hit a row, I have to go down the full table again, looking for the corresponding match to see if it is there. It is possible, as I said, that that match doesn't exist. There may be a new team in 24 which didn't play in 23. So that combination I'm looking for in 24 may not have existed in 23. Or it could have been one of the finals. You know, it is like Sunrisers playing against KKR in Chennai, and they never played against KKR in Chennai in 23. Why would they play in KKR against? Because neither of them is a Chennai team. And so it was not a playoff. Right? So we have to go through one table, and for each row on one table, we have to go through another table. So this is a version where we do 2 iterations, one inside the other. Earlier, we had 2 iterations, one after the other. Right? So we go through the table twice. Here we are saying for every row in one table, we go through the other table. Right? So if there are some 95 rows here, and there are some 88 rows here, for example, then totally we would have to do 95 times 88 comparisons. Right? For every row in the first table, I have to look at every row in the second table and compare. Right? So now this adds a significant amount of cost to our work. Okay? Because we are now having to do this multiplication of 2 sets of rows. So the number of things that we have to compute grows drastically. So how does this actually matter in sort of real world situations? Right? So here is a real world situation, which is not very difficult to imagine. So every time somebody is issued a SIM card, right, they are supposed to give their Aadhaar details. So you have to give your Aadhaar number. So therefore, every SIM card has to be linked to an Aadhaar card. Right? So there is a database, of course, of Aadhaar, and there is a database of SIM cards. But now maybe somebody wants to independently validate that the Aadhaar details for every SIM card actually exist. Right? That nobody has fraudulently created given a SIM card. No, somebody has not kind of been illegally supplied a SIM card without providing a valid Aadhaar. So we are not asking whether the Aadhaar belongs to that person. We're just saying, is that Aadhaar number real or fake? Is there a real number or not? So here we have the same situation. We have 2 tables, right? We have 2 tables. So we have one table, which is the SIM, and we have one table, which is the Aadhaar. And what we are asking is that in this SIM card table, among other things, there is one column for Aadhaar. Right? So if I look at a row in this table, I must check that this number, which is entered at the Aadhaar, appears somewhere in this table. So for every row in the SIM table, I have to scan through my Aadhaar table to make sure that the Aadhaar number entered for that SIM card is a valid SIM. Right? So this is exactly the kind of situation we did before, where we looked at compared IPL matches from one year and another year. Except in this case, these are 2 different tables. There they were the same table, but for different years. So they had the same information, but for different time periods. Here we have possibly different information. So the SIM card has a lot of information, like the phone number and something. Aadhaar has different information. But there is something in common. That is the Aadhaar number here and the Aadhaar number there should match. Right? So for every SIM card and for every Aadhaar number, we check if the Aadhaar details in the Aadhaar card are the same as those in the SIM card. If so, it is good. If we don't find an Aadhaar card that matches, this SIM card should be flagged and something should be done to make sure that this SIM card is cancelled or the person is somehow caught and apprehended and so on. Right? So the problem is the same. The difficulty is in the actual computation. So remember that we said that if we have some number of SIM cards and some number of Aadhaar cards, then in general, this will take as many comparisons as the product of the 2 numbers. Now, of course, in real life, if all the SIM cards are good, then whenever you find the valid matching Aadhaar card, right, then you would stop. So there's no need to look for the Aadhaar numbers after that because you have found the matching Aadhaar number. But the difficulty is that if there is an invalid SIM card, then no Aadhaar number matches. Okay. And if although it is not a realistic thing in this case, if every SIM card is invalid, then for every SIM card, you would actually have to look at all the Aadhaar cards before you decide. So you would actually hit M by N. Okay. So these are what are called worst case scenarios, right? So when you're calculating how long something will take, you might be lucky, right? You are looking for something and you look in the first place, you find it. Or you're looking for something, you look all over the house and you don't find it because you've actually left it in somebody else's house. So the worst case scenario is that you actually have to examine everything and then find it's not there. So here, hypothetically, okay, even though realistically it may be less than n by n, but even otherwise on an average, right? On an average, you would find the Aadhaar card somewhere in the thing and it's uniformly between the beginning and the end. So on an average, it will be halfway. So on an average, you'll have to scan half of the Aadhaar cards to find the thing. Sometimes it will be in the beginning, sometimes it will be at the end. So it's actually going to be something more realistically like m times n by 2. But m times n by 2, as we will see, is not a big help as far as what's going on here. So the question is, so what is the value of m? How many SIM cards are there? And what is the value of n? How many Aadhaar cards are there? So at this stage, it is reasonable to assume that almost everyone in India has an Aadhaar card. Okay. So without getting very precise, okay, we can say that because the population of India is something bigger than 100 crores, we can say that the number of Aadhaar cards in India is approximately 10 to the 9. Okay, 10 to the 9 is the number of zeros that you get in 100 crores. What about SIM cards? So this is somewhat difficult to answer by kind of guesswork, because of course there are a lot of people who don't have phones. In particular, there are a lot of people in this population are children. You don't expect children to have phones. So it's a little bit unclear what could be the number of SIM cards that we have to validate. But just because some people don't have phones, it doesn't mean that other people don't have multiple SIMs. Okay? So it turns out that the number of active SIM cards is approximately the same, not very different. Right? So both these numbers are actually in the range of 10 to the 9. Okay? So this means that we have to do 10 to the 9 times 10 to the 9, which is 10 to the 18 comparisons. Okay? So this nested loop runs 10 to the 18 times. So this is where now some understanding has to come about what this means. Right? So we are used to hearing that something is complicated, but computer can do it. Right? So usually we think about something which is too tedious to do by hand. And there is a kind of belief that if we just somehow manage to put it into a computer, into some automated system, it will get done. Okay? But at what scale is this actually feasible, not feasible, is something that we need to understand. So if you use a popular language like Python, right, then it can perform 10 to the 7 operations in a second. Okay, so now what is an operation? Let us be a little vague about it, but an operation is something like checking whether one number is equal to another number, or setting a number to its, so setting count to 1 plus count, incrementing. So any such thing we can think of as an operation. But there is obviously any physical thing can only do a finite number of things. So even though it is a large number, like 10 to the 7 is quite large. 10 to the 7 is 100 lakhs, 1 crore. Right? It can do 1 crore operations in a second, which seems like a mind-bogglingly large number. But we are looking at an even more large number in terms of how many operations we want to perform. Because if we are going to look at 10 to the 18 comparisons, we need to do at least 10 to the 18 operations in order to process our SIM card and Aadhaar card data. Right? So therefore, we need to do 10 to the 18 operations, and we are able to do 10 to the 7 per second. So that means we need to spend 10 to the 11 seconds in order to do this. Okay, this is all very approximate calculations. And if you might say, okay, I won't do it in Python, I will do it in a more efficient language. But even in a more efficient language, right, this 10 to the 7 will be of the order of 10 to the 8 or maximum 10 to the 9. Okay, it's not going to be much bigger than this. So we cannot the problem will not go away, as we will see when we calculate, right? So what is 10 to the 11 seconds? Let us try to understand this. Okay. So 10 to the 11 seconds, right? If you divide by 60, so 60 seconds make a minute, then you get something like 1.67 into 10 to the 9 minutes. So now if you want to calculate how many hours this is, right? Then you divide by another 60, right? And you get something like 10 to the 7 hours. And now you divide by 24, and you'll get something like 10 to the power 6 days, right? And now if you divide by 365, you get 3,200 years, right? So this is saying that if you really want to validate the SIM card database, then it's going to take you 3,000 years to do it on a computer. And notice that if I take a language which is 100 times faster, okay, than Python, this will go from 3,200 years to 32 years, which is not much better, because anything which is going to take decades is clearly something that we cannot do feasibly. Right? So as such, these are the kinds of questions which are relevant for people who study computational tasks and try to decide whether or not they can be made more efficient, because if they don't make it more efficient, then some tasks are simply not feasible, even if the automatic processing power of a computer is available. Right? So what could we do? So let me switch to another problem. Right? So supposing I ask you to guess my birthday, right? So I want you to tell me what day and month of the year I'm born. And the game is that you propose a date, right? And I will either say, yes, you have guessed the right date. Or I will say, no, you have not guessed the right date. My birthday is earlier than the date you have guessed. Or I will say it is later, right? So either I say yes, or I tell you whether your guess is too late or too early, whether the actual birthday is earlier or later. So for example, supposing my birthday happens to be the 12th of April. Okay. Perhaps you might start off with a guess saying September 12th. So I would say, no, it is not September 12th. It is earlier than September 12th. So now obviously your next guess should be between September 11 and January 1. There's no point in ask me now, is it November? Because I've already told you it's before September 12. So perhaps now you tell me February 23rd. So now I tell you, no, it's later. So now what is your thing? It is between February 24th and September 11th. Right? So this is your possible guess. So you give me another guess and we go on. So you say July 2nd, I'll say it's earlier, and so on. Right? So eventually, hopefully you will come down to it. So what are we doing? We are starting with some range, which is January 1 to December 31. So depending on whether I tell you I was born in a leap year or not, this starts from 1 and goes to 365 or 366. Right? And now you give me a guess. Right? And then what happens there is then the possibilities get narrowed. And then you give me another guess. And now the possibilities get narrowed to this rate. And then you give me another guess. And now the possibilities get narrowed to this rate, and so on. Right? So you're shrinking the range of values, and eventually this has to come down to a narrow enough interval where it's only one date, because unless I was not born, and I'm lying, right? There must be a date which is valid, which you will eventually reach. Of course, you could have done it one at a time. You could have said Jan 1st, then Jan 2nd, then Jan 3rd, and so on. But this is not efficient. So what do we want to do? We want to make the shrinking process fast. So what is the best strategy for asking these questions? So you have this interval, right? So the best thing that you can do, so notice that if I put a question here, which is to the right, if the birthday happens to be later, then I have reduced it to a much smaller interval. But I don't know whether it's going to be later or before. So if it's here, I have a much bigger interval. Right? So again, going by the principle of looking at what could happen in the worst case, the worst possible scenario. You would like the worst possible scenario to not affect you badly. So if you want to make the worst possible scenario not affect you badly, you want to make the worst case as small as possible. So what you would do is you would shift this so that it is roughly midway. So that means that whether I ask you to look before or I ask you to look after, in both cases, you are looking at approximately the same number of days. So you have reduced the interval to the same size, no matter what the answer is. I mean, of course, you could be lucky. It could be that the point you have chosen is the answer, and then there's no problem. But if you do not get the answer, you would like your next question to be as reduced as possible with respect to the previous question. So the best choice is actually to halve the interval. Right? So if we were doing this birthday thing, then roughly we would pick the middle of the year. Right? So either June 30th or July 1st, if you carefully calculate which one it is. It could even be July 2nd, I'm not very sure. You pick that date. Right? So then I say it is earlier, the same, I'm still targeting this 12th April, right? So I say it's earlier. Then if it's earlier, then you take the interval from January 1st to June 29th. So roughly 3 months. So you take the end of the third month, say March 31st. So I say it's later. Now you're looking from April 1st to June 29th. So midway is, there are 3 months. So you're looking at 1.5 months, so May 15th, right? And then May 15th, I say it's earlier. So now you're looking at 1.5 months. So you want, 3 by 4 of a month. So roughly 3/4 of the way through April. So you would say something like April 22nd, right? And then I tell you it's earlier. Now you're looking between April 1 and April 22. So I say April 11, yeah, and so on, right? So you basically converge. Okay. And how many steps does it take you to converge? Well, notice that what you're doing is that you're shrinking this thing by half, right? So 365, then you pick one, then your 364 options are there. They're equally divided. So you have the next thing is going to be 182. 182, you pick one, then it could be either 91 or 90 because they are 181, right? After this, you pick one, then you are left with 181 choices. So one side, the worst case is 91. So you have 91 and go on. So in this case, you will always, and this is the important thing, you always stop in 1, 2, 3, 4, 5, 6, 7, 8, 9 steps. Right? So you cannot ask more than 9 questions without finding the answer if you follow this strategy. So it's under 10 questions, okay, in this case. So how do we, so what is the key property, by the way? The key property is that the birthdays are in some order, right? So if I have all the possible birth dates, and if you ask me a birth date, the remaining birth dates are either after that or before that. So if I say it's before, then you can rule out everything that is after. If I say something is before, you can rule out everything that is after. You can rule out everything that's before. And this is crucial. Okay? If something is not sorted, if I look at the first, supposing you take a shelf full of books, and you're looking for a title, and the books are not arranged in any particular order. Right? If I tell you that the middle book is not the book you're looking for, it doesn't tell you anything about whether to look on the left side or right side of the shelf because the books are in no order. But if I tell you that the books are arranged in, say, alphabetical order of the author, and if you look at the middle book and you find that the author's name that you are looking for is earlier in the alphabet than the book that you see in the middle, then you know that the book you're looking for must be in the left half. Right? So because the information is in an order, we are able to use this midpoint to decide whether to focus on the left half or the right half. So if it is not ordered, right? So this is something which is important to, so if it is not ordered, right, I must so supposing the book I'm looking for, somebody has borrowed. So I'm looking on a library bookshelf and I'm looking for a book and I don't know whether somebody has borrowed this book. Unless I look at every book in that shelf, I cannot be sure that the book has not been borrowed if the books are not sorted. But if the books are sorted, right, I can examine a very small number. So in this case, 365 days, with examining 9 dates, I was able to find the answer, right? Compared to 365, that's a very small number. So a very small number and still figure out it's not there, right? So this is quite remarkable, right? So if I replace this birthday thing by 365 books, you have 365 books arranged on a shelf in alphabetical order. I want to find a book, looking at only 9 books. So I don't look at 356 books, and still I can tell you my book is not there, right? So that's quite a remarkable. So therefore, suppose we assume that the Aadhaar information that we were trying to resolve is actually sorted by Aadhaar number. So when we are looking for the Aadhaar number for a given SIM card, we don't necessarily have to start from the beginning of our Aadhaar list and go down, right? Earlier, what we said is we had this SIM card thing, right? And when we had a row here, then we had to go to this Aadhaar thing and start at the beginning and go to the end, because we had no information about how the Aadhaar database is how the list is ordered. So it could be anywhere. But now let's assume that the Aadhaar is actually sorted by the Aadhaar number, right? So then what we will do is that we would essentially do this clever searching that we did, right? So we use this halving strategy. So we would take the SIM card, right? And then we would take this Aadhaar database, and then we would first look here in the middle. And then this will tell us either to go up or down. So if it tells us to go up, then we would look at this point, and so on. Right? So by halving the space that we look at, right, we would arrive at the answer. So how long will this halving take us? Okay. So if we halve 10 times, then we are dividing by 2 10 times, and 2 to the power 10 is 1024. So we're actually dividing an interval of size 1000 into 1, right? So 1000 goes to 500, goes to 250, and so on. So after 10 steps, you will have to come to 1. Okay? So in 10 steps, I can reduce the interval by a factor of 1000. So in 10 more steps, right, I would reduce by a factor of 1000 times 1000. And then after 30, right, so after 10 steps, I have 10 steps. 10 to the 9 has become 10 to the 6. Right? After 20 steps, this 10 to the 6 will again reduce by 1000 factor, so it will become 10 to the 3. After 30 steps, right? So 10 to the 3 will reduce by a factor of 10. 10 to the 3 will come to 1. Right? So after 30 steps, I have actually reduced the choice of Aadhaar card to 1. And this is where it's important, because unlike the birthday, where I was confident that the person who asked me the question was not lying, they have a birthday, here it is actually possible that the SIM card is a fraud. Right? So it may not be any Aadhaar card. So when I shrink it down to 1, if that is not the one I need, then I know it's not there. So by looking at only 30 Aadhaar numbers out of this 10 to the 9 possibilities, I'm able to decide whether I found it or I've not found it. Okay? So now the problem has become tractable, because now for every SIM card, I need to take 30 Aadhaar numbers and look them up. So the total time that I need is 30 into 10 to the 9. That's the total number of steps. Earlier it was 10 to the 9 times 10 to the 9. And if I take 30 into 10 to the 9, right, this is like something of the order of, so remember it is 30 into 10 to the 9 divided by the fact that my Python thing could do 10 to the 7 operations in every second. So this gives me 3000, right? And 3000 seconds if you divide, okay, so 3600 seconds will be an hour. 3000 seconds is about 50 minutes. Okay, 600 seconds is 10 minutes. Okay? So instead of spending 3200 years, you have solved this problem in 50 minutes. And if you have a 100 times faster computer, it will solve it in half a minute. And this is eminently doable. Even if it takes 50 minutes, you can start this computation, go and do something else, come back and check after an hour, and the job is done. Okay? And remember that this is a kind of a task which you will have to keep doing again and again with different data, because people are getting SIM cards all the time, and people are also getting Aadhaar cards all the time. Right? So it's not that these lists are static. So you need to be able to do this repeatedly, and you cannot afford to spend thousands of years. right? So this is an illustration that you need to do something, and this is what I talked about earlier. So this is called pre-processing, right? So you want to search through the Aadhaar list, but searching through the Aadhaar list as it is given to you may not be helpful. So you want to actually arrange the Aadhaar list in a sorted order so that you can exploit the searching property of doing half at a time. Right? So this now hopefully gives you some background on what different aspects of computational thinking are. So just to end the talk, I will end with a story on a lighter note, which goes back to the idea of computational thinking in real life. Okay. So this is a story which is actually due to very well-known computer scientist called Edgars Dijkstra. So some of you who have studied some aspects of computer science might know he is well known for something called the shortest path algorithm. So Dijkstra was one of the pioneers in modern computer science. He worked primarily in the 1960s, 70s, 80s. And he was also well known to be very opinionated, as you will see from this story. And he used to write a lot of what in modern day parlance would be called blogs. But he used to write these manuscripts. So he often used to travel to various places and conferences and so on. So he used to write these stories, and some of them were technical and some of them like this were non-technical, but they had a point, right? So in this story, he says that there was a railway company, right? And they used to have trains in which every coach had a toilet at one end, right? So toilet at one end. So if you are familiar, right? So you should think Vande Bharat, right? So Vande Bharat has toilet only at one end. Okay? So they used to have coaches like this. Okay? So now somebody in the management of this railway company said that these toilets are actually wasting space, right? Instead of having a toilet, you could put seats, and therefore you could sell tickets. And do we really need, toilets in every coach? People can walk a little bit, and these are short journeys and all that. So why don't we just reduce the number of coaches with toilets to 50%? So half the coaches in every train will have a toilet at one end, half of them will have no toilet. So now what happened was that this instruction was not kind of communicated. So 50% of all coaches overall had toilets, but you have to make sure that each train has 50%. So some trains had no toilets at all. Some trains had all coaches with toilets. Right? So there were a lot of chaos. Passengers were very unhappy. So they said, okay, we will mark outside whether each coach has a toilet or not. So we will put some kind of a mark on it. And then people who are shunting these trains to compose a rake before the train goes will be told to make sure that half of the coaches have toilets, half of the coaches do not have toilets, so that each coach has 50%. But this is not enough. Okay? So first of all, it makes the problem complicated because you have to keep this in mind when you compose these trains. But this is not enough, because it's not enough to say that the trains have 50% toilets, right? So the 50% toilets must be equally spaced out. So if you have all the toilets at one end of the train, then the other half of the train, people have to walk a long distance. So again, there was a lot of dissatisfaction among passengers. Right? So then they said, okay, make sure that they alternate. Right? So this is still more work. Now you have to not only put together these trains with 50% toilets, but you have to make sure that they alternate between those with toilets, those without toilets. Right? But now you could have the problem that the coaches look like this. So I have a coach. Right? So I have 3 coaches in a row. Right? And I have a toilet here, and I have a toilet here. So now supposing you are here and you start walking looking for a toilet, you might end up having to go a long way. Right? So again, this is not satisfactory. So now they said, okay. Then you make sure that all the toilets point the same way. Right? So you make sure this doesn't happen. So now not only are the coaches outside marked with a T, but their coaches are marked with a T and an arrow. Right? So now they have to make sure that these coaches are rotated, so all the arrows in the train point in the right direction, and the T coaches are, together, are alternate, and so on. Right? So even now there is a problem, because if you have inside the coach, there is no marking, right? So outside the coach it says this, but inside the coach you don't know this. So you might be sitting here, right, and the nearest toilet may be to your right, but you end up walking all this way. Right? So now inside the coach, so inside which coach? Now you have the coach which has the toilet. This coach, of course, you know where the toilet is. But now inside this coach, you have to say the toilet is in that direction. So both the toilet coaches and the non-toilet coaches now have an arrow, and they all have to be put in the same direction. Right? So at this point, the whole system broke down. Right? So they were given all these instructions, all these coaches had all these arrows, everything had to be put in the right direction, everything was messed up. Right? So everything was, so this is the case where, like the problem we had before, you had to do something, but the time it took in order to process all this information and to put these coaches together was so long that the schedules could not be met. Okay? So then somebody came up with this bright idea. They said, why don't we just take a coach like this, a coach like this, right? Make sure that the toilet sits in the middle, and make sure that this guy has something which points that direction. So inside both these coaches, they know that the nearest toilet is in this direction. Okay? So now you don't make coaches out of trains out of single coaches, but you make them out of pairs of coaches with a toilet in the middle. Right? So now you have a pair of coaches. They could be, it doesn't really matter whether it is this way or the other way around. Right? It's just a little bit of whether you cross the center or not. They're essentially identical. So now we have come back to the situation we had in the beginning. In the beginning, we said that every coach had a toilet at one end, and inside, of course, you know which end it is. So you could walk to the nearest toilet. Now every pair of coaches has a toilet in the middle, and everybody knows where the toilet is. So it's not exactly the same, because now you can't have an odd number of coaches, but the whole problem is solved. Okay? So now comes the point of Dijkstra's thing. So he said, so this, according to Dijkstra, is, of course, in those days, the word computational thinking did not exist, but he would call it today an instance of computational thinking. Right? So the person who found this solution, according to Dijkstra, deserves to be called the world's first competent program. But then, of course, as I said, Dijkstra is a controversial person, so he goes on to say more things. So he said that programmers are, of course, delighted by this story. So anybody who has programmed is happy with the story. Then he also goes on to say that managers get more and more annoyed as the story progresses. And then finally, he comes up with this very negative statement saying mathematicians don't see the point. Okay, so this, remember, was about 60 years ago. I think, as we discussed in the beginning, as was introduced by Anuja, I think now mathematicians do see the point, right? So the computation is important. It is a very relevant part of a lot of research mathematics now, to do computational tasks, to validate conjectures or to look for patterns and so on. So I think the idea that we need to do efficient computation in order to progress, both for the sake of day-to-day problems that computer scientists worry about, but also for the sake of mathematical problems that mathematicians do worry about, is something which is important, and we should keep that in mind. So thank you for listening patiently, and I'll be happy to take any questions.
Thank you, Professor Mukund, for the wonderful talk. It was truly insightful. Now we are moving to a short segment of interactive session. So here, participants can ask your questions. Please turn your video on and introduce yourself before asking your questions. Or maybe if they are not in a position to speak right now, shall I read the question, sir?
Yeah, guys, I saw the question now. So
Okay.
it says about proofs. The question is, I wish to seek guidance on how we should develop computational thinking so as to enrich our thought processes and help with our general approach to mathematics. So I think that, as I said, there is not a direct correlation between the idea of computational thinking and the idea of doing some mathematical research. So computational thinking is not necessarily going to help in terms of your ideas about what you are doing in mathematics. But on the other hand, as I said, if look, depending on the kind of problem you're trying to solve, being able to use these, so there's a lot of actually software now which is written from the perspective of mathematics, and it can do, abstract number theory, it can do abstract group theory, linear algebra, and all these things. So if you have some familiarity with how to work with these tools, you can greatly expand your ability to explore examples, counter examples, and use that as an exploration tool. So computational thinking will not necessarily improve your intuition directly into the mathematics that you're trying to solve, but by indirectly, by looking at more complicated examples and with more cases, you might get new ideas about what you're trying to do. So it can be an assistant, but it's not going to directly give you some new insights into how to prove your theorem. That you still have to do yourself.
Thank you, sir. I think Neha can't speak at the moment, she messaged. And adding to that, she's also asking about the platforms or tools that can be used for mathematical purposes.
Yeah, so there is one open software, free software platform called SAGE, S-A-G-E. So that is incorporates, so it is an attempt actually to create one comprehensive package, which, as I said, there have separate packages for all these different types of mathematics, commutative algebra or group theory or number theory. So SAGE brings all of these together so that everything is available in one single thing, and it uses Python as a language where you can add your own, you can use these things and combine them. So SAGE is the best place to start if you want to look at computation from a perspective of a research mathematician. And as I said, it's a free and open tool, so you should be able to get it without any cost.
Okay, sir. Thank you so much. Now I invite anyone who wants to ask a question.
Hello. I'm really sorry, sir, for interrupting. I just wanted to ask one thing, that when you said proof, do we need rigorous proof, like in real analysis we have to prove, like in theoretical computer science we need proof like that?
Computer science proofs are rigorous in the same way that mathematics proofs are, because you have to have a logical argument which is kind of and it's not always possible. As I said, sometimes it is not possible. So sometimes there are computational ideas which work well in practice, so to speak, but people are not able to actually justify why. So so there is a certain part of computer science where people are using some ideas which work well, but which cannot be rigorously proved. But especially something like this, if you want to show that something cannot be done, then you have to prove it, right? So if you have so you may come up with an algorithm which works, but you may not be able to establish its best possible performance level. So at that level, you may not have a proof, but at least you should be able to show that it gives the right answer. There's no point in efficiently giving the wrong answer, right? So you might have a thing which works well in practice. You don't know when it is not going to work, but at least for most normal cases it works. You may not be able to prove how well it is. But if you want to say something is not possible, you have to do it.
Okay.
So I think Sayak is going to talk for some time, so maybe you are.
Hello, sir. Can everyone hear me?
Yeah.
Yeah. Hello. It was a very nice talk. And yeah, I've heard of Dijkstra. By the way, my name is Sayak Sengupta. I completed my PhD in mathematics a year back. Right now, I'm looking for assistant professor positions in India in mathematics. Well, before starting the PhD, I would say that I was not very interested in computational thinking and computational methods. But my PhD problem, well, not at the beginning at least, was not really part of computational thinking procedure. But at the end, I had to use some algorithms which I developed with my advisor. And that ultimately led to a lot of finiteness ideas. I was able to boil down the problems into finitely many pieces, so to speak, and then group together and then use Python in order to calculate the most efficient way to address the problems. So my problem was actually about calculating orbits of polynomials, and basically try to understand. So it was a classification problem, so to speak. And you start with a number, let's say given number, let's say 5, for example, and then you consider all the polynomials and the orbits of those, which will eventually disappear at 5. So u of 5, u of 5, and so on. And at certain point, of course, after finitely many steps, you will see 0. So classify all such polynomials that way. And I was able to develop some algorithms using some ideas. And that led to an inductive process. And where right now I'm just trying to get some sort of code so that I can put it in the machine and try to posit some sort of conjecture. Because right now all I have are some discrete results, which is a lot dependent on inductive process. So I have everything done up to n equals 4, n equals 5, and so on, up to n equals 7 or something. But when I was trying Python for n equals 8 or n equals 9, it was taking a lot of time. So some efficient methods and efficient algorithms needs to be developed in order to address those. And that's what I'm trying right now. So I definitely have received a lot of influence from your examples that how this sort of sorting algorithms can help. And you were talking about Dijkstra, so I didn't know about Dijkstra before, but I was taking geometric invariant theory course at certain point, and Dijkstra's name came up. I think it's the same Dijkstra. And yeah, but there's something similar to what you said, where I also said in that course about how algorithms were different and somewhat unique in some aspects. So yes, so I really enjoyed your talk, and it was amazing.
Thank you. And all the best with your conjectures.
Thank you.
Thank you, everyone. So I guess we are moving to the last part, vote of thanks. And I should say the audience participants, you were really wonderful, so active and energetic. Before moving to the vote of thanks, Tamban sir, might I ask if you have any comments to make before we finish?
Yeah, maybe Mukund, I have some general query. These mathematicians have the tendency to look for a general kind of things. Suppose you have a specific methods for problem-centric, some procedures. That itself will be, of course, for a specific task, it will be very important. But the mathematicians generally have a tendency to generalize it.
Yes.
Why not this? Why not this? Sometimes you neglect these specific things. You go for a general things. I mean, so what is your opinion about this? Is it, of course, I mean, it all depends again, a balancing act, but.
No, so I think especially, I mean, if you look at this area which I talked about, this computational complexity theory, where you're trying to show broadly speaking, it's talking about classifying groups of problems. Saying these problems can be done efficiently, those problems cannot be done efficiently. So that is in some sense in the same spirit that you're solving something at a general level. You're saying if the problem looks like this, it will have this, or if it has this kind of a structure, it will be efficient, and so on. But of course, what happens, and it's the same thing that happens in mathematics also, that sometimes you're not able to prove it, and then you put some restriction, and that's saying. So it is very similar in flavor to the kinds of studies that you do, except the structures you're looking at are not as well defined as mathematical structures. But that consideration certainly comes, especially in these kind of areas, which are more. So when you're looking, as you said, at algorithms for a particular problem, it's hard to generalize with the same technique. It's in fact, it can be a source of frustration also, because you don't know whether this technique will be applicable in a similar problem with slightly different things. But at the other end, when you're looking at these either impossibility results or classification results, definitely it's the same flavor. And there has been a lot of that kind of thing. It's similar to, you look at Riemann hypothesis, you don't know how to solve it. Then you say, assuming Riemann hypothesis, you can solve something. So you have this whole hierarchy of things in computer science also. Assuming that these two things are different, then something else is true, and so on. So the whole sort of conditional results, some specialized results. But the main goal is to prove the very general statement, which seems very elusive Of course, computer science is not as old as mathematics, so you can't say for certain, but some of these problems are now by computer science standards very old. They are some 50, 60 years old and they have not been solved. So, and these are also problems which are like that packing problem. It's not that the problem was not invented after computer science. People have been looking at such problems from a practical perspective for centuries. And so if nobody has yet come up with something efficient, it suggests that there should not be. But the problem is to find a mathematically rigorous argument for it. And that seems to be very hard.
Yeah.
But yes, so the spirit is very much the same.
Yeah.
In some areas.
Yeah, we see, for example, I work in an area called regularization theory. So this is used everywhere in machine learning here, there, etc. But the people like me is doing in the operative theoretic, and people tend to generalize in a more.
Yeah.
I mean, sometimes you lose the connection with the actual thing where the so-called applications are lying, right?
Yeah,
So
that's true.
that tend to happen is. Okay. Thank you. Anyway, it's a nice introduction to many new things. Even people like me could get it. Thank you.
Yeah, I'm happy that it was useful. Thank you.
Yeah. Thank you.
Thank you so much, Tamban sir. Now let's move to the final thing, our vote of thanks. Let me welcome my dear friend, Miss Unnati Shukla, research scholar, IIT ISM Dhanbad, for delivering the vote of thanks for the program.
Thank you, Ajuna. Am I audible?
Yes.
Okay. So first and foremost, happy Pi Day to all of you. And thank you everyone for being a part of this webinar. My name is Unnati and I'm an active contributor and teacher in this community. It is such an honor for me to get this opportunity to thank all the dignitaries, contributors and participants of today's event. First of all, I would like to thank Professor Madhavan Mukund sir to take time from his busy schedule and grace the event. So you started off with a very basic example to explain the basics of computational thinking. Your introduction to counter variable, max variable was a refreshment for me about all the programming basics. You talked about shrinking the interval, using the midpoint and optimizing time. It was such an astounding concept, reducing the time from 3,200 years to like 50 minutes. It was amazing. The toilet fix problem was also amazing to hear. There were so many new concepts and ideas that you introduced us to. It has encouraged me to know more about this subject, computational thinking. A special thanks to Ms. Ajuna, our host. She has managed to maintain the curiosity and enthusiasm from the start to the end. I would also thank Mr. Tamban Nayan sir, formerly professor and head Department of Mathematics, IIT Madras, and currently a visiting professor at BITS, Goa and Pilani, for introducing our speaker. Also, I'd like to extend my gratitude to Bijumon sir, Associate Professor, M.G. College, Iritty, Kerala, for continuous technical support to the community. I would also thank Ms. Shikha Kumari, Research Fellow, IIT Mandi, for the amazing promotional video that she made. And finally, my heartfelt gratitude to the founder of this great community, Vinod Kumar sir, Associate Professor, TMG College, Tirur, Kerala, whose initiative has connected all of us together today and from the past few years. In this, in the end, my thanks to our active contributors, Ms. Gayathri, Research Fellow, IMSc Chennai, Ms. Rosna Paul, Graz University of Technology, Austria, Ms. Amrita Warrior, Research Fellow, IIT Madras, Ms. Gayathri UC, MSc student, NIT Calicut. And last but not the least, a big thanks to our enthusiastic audience for joining and making this event a huge success. Thank you everyone. Yes, over to you, Ajna.
Okay, now I thank you, Unnati, for doing the delivery of vote of thanks. So we officially wind up the session.